Take the smallest speck you can picture. Now shrink it 1,000,000,000,000 times, then 1,000,000,000,000 times again. Keep going. Somewhere down there waits a wall, a size so small that space itself stops making sense. Scientists call it the Planck length, and it may be the true bottom of reality. Below this point, the rules break. Space begins to bubble and boil. A ruler this tiny would collapse into a black hole, and the word distance loses all meaning. Today, we shrink past atoms, past the pieces hiding inside them, down to the smallest step the universe will allow. If wonders like this keep you curious, subscribe and come along. We are about to touch the edge of everything we know. Hold on tight. We begin. Picture a scientist staring at a single number scribbled on a page. The number is so small it barely looks real. Below it, nothing. No smaller distance seems to mean anything at all. That number marks a flaw, a bottom to reality. And the strangest part is that the universe seems to have built this flaw on its own, long before any person came along to measure it. We live our whole lives thinking distance can shrink forever. Cut a piece of string in half. Cut the half in half. Do it again. Your scissors give up, but in your mind you can keep going. Smaller and smaller, with no end. For most of history, that felt like plain truth. Space was smooth. You could always slice it thinner. There was always a next step down. Then physics found a hidden wall. At a size unthinkably small, the ordinary idea of distance stops working. Ask what sits below that wall, and nature seems to shrug. The question turns to fog. Every tool you might build to measure it breaks the moment you switch it on. This wall has a name, the Planck length. It sits at the far bottom of the small, the same way the speed of light sits at the far edge of the fast. A hard limit stitched into the fabric of the world. Think of a digital photo on your phone. Zoom in, and the picture holds sharp for a while. Keep zooming, and suddenly you hit the pixels. Little squares. There is no image hiding inside a single pixel. That square is the smallest piece the photo has. Some scientists think reality has its own version of a pixel, and the Planck length is how wide it might be. Here is the part that should stop you cold. This is not a limit on our machines. It is not a problem we could fix with a bigger budget or a smarter lab. Down at this size, the two greatest theories in all of physics both collapse. The math that runs the stars and the math that runs the atoms both throw up their hands and refuse to answer. That has never happened anywhere else. Everywhere we look, from exploding stars to spinning galaxies, our theories keep working. Sometimes they strain, sometimes they surprise us, but they answer. At the Planck length, for the first time, they go silent together. Scientists are certain the number is real. They can write it down. They can point to where it comes from. What waits below it stays a mystery, one of the deepest in all of science. And chasing that mystery leads somewhere wild. It leads to space that bubbles like boiling water. It leads to tiny black holes that flash in and out of being. It leads to the very first instant after the Big Bang, when the entire universe was squeezed down to this exact size. But before we go down there, you need to feel how small this really is. And once you do, the number stops looking small. It starts looking impossible. Say the Planck length out loud, and it sounds like a joke, a tiny distance, but your mind cannot picture it, no matter how hard you try. So let us walk down together, one step at a time. Start with something you know, a single human hair, about as wide as anything you can see without help. Now, zoom in 100 times, and you reach a red blood cell riding through your veins. Zoom in 1,000 times more, and you find a single atom. Already you have left the world of the eye far behind. An atom is so small that a line of them across the width of that hair would number close to 1 million. Feel free to stop and breathe. We have barely started. Now dive into the atom. Almost all of it is empty space. Way down in the center sits a nucleus, a tiny, dense core. To picture the gap, blow the whole atom up to the size of a football stadium. The The nucleus would be a single pea sitting on the 50-yard line. Everything else, empty. That pea, the nucleus, is already unthinkably small, and we are nowhere close. Crack the nucleus open, and you find protons and neutrons. Crack those open, and you find quarks, some of the smallest bits of matter we know. A quark is so small, we cannot even measure its true size. Our best machines say it is smaller than 1/10,000th the width of a proton, and maybe far smaller than that. Surely we must be near the bottom now. We are not even close. Take that quark, that speck at the edge of everything we can measure, and keep shrinking, not by a little, by a factor so huge it breaks the mind. The Planck length is smaller than a quark, by roughly the same amount that a quark is smaller than the entire solar system. Read that again. The jump from a tiny quark down to the Planck length is like the jump from the whole solar system down to that same tiny quark. The scale folds in on itself twice. Here is another way to hold it. Imagine an atom blown up to the size of the entire observable universe. Every galaxy, every star, all of it, stuffed inside one atom made giant. Even then, at that insane scale, the Planck length would be about as wide as a normal tree. Small, ordinary, lost in the vastness. Numbers stop helping at this point. The distance is so far below anything your senses have ever touched that your brain has no shelf to store it on. And that is exactly why it matters. We are looking at a size that lives beyond every picture, every comparison, every ruler ever made. A place where our best words run out. So where did this impossible number even come from? Who first wrote it down? And why did they trust it? The answer traces back to one quiet man, working alone with only 3 simple numbers borrowed from nature herself. And what he found scared even him. The year is 1900. A German physicist named Max Planck sits with a problem that has nothing to do with tiny distances. He is trying to understand how hot objects glow, why a coal ember shifts from red to orange to white as it heats. To crack it, Planck does something bold. He guesses that energy does not flow in a smooth stream. Instead, it comes in tiny packets, like coins, instead of a liquid. This single guess kicks off the entire field of quantum physics and changes science forever. But that is not our story. Our story is a side quest. Planck took almost as a game. Planck noticed something strange about the deep constants of nature. These are numbers that never change, anywhere in the universe. He had 3 favorites. The first is the speed of light. Nothing outruns it. It sets the top speed for everything that moves. The second describes gravity, the pull between all things with mass. It says how strongly the Earth holds you to the ground and how strongly stars hold their planets. The third is his own new packet number, the one that rules the quantum world of the very small. Planck wondered what would happen if he combined these 3. He played with them like puzzle pieces, multiplying and dividing until the units of speed and mass and energy all cancelled out. What fell out the other side was pure, a length, a time, a mass, numbers built from nothing but the bones of the universe. Think of it like baking. You take 3 basic ingredients that seem to have nothing in common. You mix them in just the right way, and out of the oven comes something no recipe told you to expect. The length that fell out was almost impossibly small. The Planck length. The time that fell out was the blink to end all blinks, a slice so short that light itself barely moves across it. What thrilled Planck was where these numbers came from. He did not measure them in a lab. He did not pick them to fit some experiment. They came straight from the raw constants of reality. That meant an alien on the far side of the galaxy, working with the same 3 numbers, would get the exact same answer. This length belongs to the whole cosmos, not to Earth. Planck himself called these natural units. He believed they would keep their meaning as long as the universe lasted, for any mind anywhere clever enough to find them. Yet even Planck did not fully grasp what he had touched. To him, it was a beautiful pattern, a clever bit of math. He had no idea that this tiny length marked a doorway, a place where space and time themselves might come apart. That deeper meaning would wait decades until other scientists looked closer and felt a chill. Because here sits the puzzle. Planck built this number from gravity and the quantum and light. And gravity and the quantum are the two things in all of physics that refuse to get along. When you force them to meet, at this exact size, they go to war. The map that guides the stars and the map that guides the atoms both point to this one length. And there, at the bottom of the small, they crash into each other. To feel why that crash matters, we first have to ask a stranger question. Why would the universe bother to have a smallest size at all? Here is a thought that keeps physicists up at night. The Planck length was never voted on. No committee chose it. No king decreed it. It falls out of the universe on its own, whether we like it or not. Compare that to the tools we use every day. The mile came from Roman soldiers counting steps. The foot came from an actual foot. These sizes are human. We made them up to fit our lives, and we could have picked others. The Planck length is different in a deep way. It hides inside the constants that shaped the cosmos before the first star ever burned. Change nothing, invent nothing, and it is still there, baked in. Why should reality have a smallest step at all? Why not let space shrink forever, smooth and endless, with no floor to hit? The answer comes from a fight between two of nature's own rules. The first rule comes from the quantum world. To look at something small, you have to hit it with light or particles, and the tinier the thing, the more energy you need. To see a tiny distance, you need a huge blast of energy squeezed into a tiny spot. This is a hard rule, not a habit. The small demands the mighty. The second rule comes from gravity. Pack enough energy into a small enough space, and that space collapses. It folds in on itself and becomes a black hole. This too is a hard rule, tested in the hearts of dying stars. Now watch the trap close. To see down to the Planck length, you would need so much energy in so small a space that the two rules collide. The energy needed to spot the distance is exactly the energy needed to crush that spot into a black hole. The moment you switch on your perfect microscope, it swallows the very thing you were trying to see. Picture trying to study a snowflake by holding it in your bare hand. The only way to see it clearly is to bring it close to your warm skin. But your warmth melts it before your eyes can focus. The tighter you look, the faster it vanishes. The Planck length works the same cruel way. Looking closer destroys the thing you look at. So the universe seems to guard a bottom floor. Below the Planck length, the very idea of distance may simply stop, not because our eyes are weak, but because reality itself refuses to hold a smaller ruler. Scientists are careful here. They agree the Planck length is where our theories die. Whether it is truly the smallest possible size, a hard pixel of space, or just the point where we go blind, stays an open mystery. Some believe space really is grainy down there. Others think it stays smooth but forever hidden. The debate is fierce and far from settled. What everyone agrees on is stranger still. Something special happens at this size. A wall, a veil, a line the universe draws around its own deepest secret. And that raises a question that sounds almost silly until you sit with it. If you actually built a ruler and tried to shrink it down toward this wall, what would happen to the ruler itself? The answer breaks the ruler in a way no hammer ever could. Grab a ruler, a plain one, the kind in a school desk. It measures inches and feet, simple and solid. Now imagine we could shrink it, not the numbers on it, the whole thing, smaller and smaller, so it could measure tinier and tinier gaps. For a long while, the shrinking goes fine. Your ruler measures the width of a cell, then an atom, then the space inside an atom. It keeps working, faithful and true. Then trouble creeps in. To mark off a distance, a ruler needs edges, sharp, steady lines you can trust to sit still. But down in the quantum world, nothing sits still. Every tiny thing jitters and shakes, buzzing with restless energy that never stops. Your ruler's crisp edges start to blur, like letters seen through tears. Keep shrinking, and it gets worse. The marks on your ruler need to be made of something. Atoms, then pieces of atoms, then whatever lies below. But those pieces are now bigger than the distance you are trying to measure. It is like trying to measure the width of a hair using a ruler whose smallest mark is a mile wide. The tool has become clumsier than the thing it measures. Push down toward the Planck length, and the ruler faces its final doom. Remember the trap from before. To pin down a distance this small, you must squeeze in a wild amount of energy, and squeezed energy warps space. At the Planck length, the energy needed to make one clear mark is enough to bend space into a black hole right at the tip of your ruler. So your ruler does not just blur, it does not just get clumsy. Its own measuring tip collapses into a tiny black hole and swallows itself. The harder you try to read the smallest distance, the more surely you erase it. Think of writing your name in wet sand at the beach. Press too lightly and you leave no mark. Press harder for a clearer line, and the sand caves in and fills the groove. Press harder still, and you dig a pit that swallows the whole word. At some point, no matter how you try, a clear mark simply cannot survive. The Planck length is where the sand of space always caves in. This is why scientists say the Planck length may be the smallest meaningful distance, not because we lack a fine enough ruler, because any ruler that fine destroys the very distance it tries to show. The concept of a smaller length loses its grip on reality. Let that settle. We are used to thinking measurement is always possible in theory, even if it is hard in practice. Give us a better lab, a bigger machine, more time. But here, nature slams a door. No lab, no machine, no amount of time can read below this floor. The limit lives in the rules of the universe, not in the size of our wallets. Physicists are confident about this wall. It shows up in every serious attempt to join gravity and the quantum. What lies beyond it, if anything, remains one of the great unknowns. And this leads to an idea so odd it sounds made up. To see the smallest thing in the universe, you would first have to create the most extreme thing in the universe. To glimpse the Planck length, you would have to build a black hole. Let us find out why. To see something, you shine light on it. That is how eyes work, how cameras work, how every microscope on Earth works. Light bounces off the thing, comes back, and paints a picture. But light has a hidden limit. It comes in waves, like ripples on a pond. And a wave can only reveal things bigger than itself. Try to spot a pebble with ocean swells rolling past, and the pebble hides in the water. The ripples are too wide to feel it. To see something small, you need small waves, tight, quick ripples that can trace the edges of tiny things. And here is the catch that changes everything. Smaller waves of light carry more energy, much more. The tinier the wave, the harder it punches. Ordinary light, the kind you see, has fairly big waves. To peek at an atom, scientists use waves far smaller and far more powerful, like X-rays. To peek at the pieces inside an atom, they need waves smaller still, packing a ferocious punch. Follow that path all the way down to the Planck length, and the numbers explode. To make a wave tiny enough to trace something that small, you would have to cram in a truly monstrous amount of energy. More energy in one point than a star pours out in ages. Now remember gravity's iron rule. Pile enough energy into a small enough space, and that space collapses into a black hole. It cannot help it. The energy bends space around itself until a trap forms, a pit that not even light escapes. So, picture the moment you finally build your perfect Planck microscope. You focus your beam. You pour in the energy needed to see that impossibly small distance. And at the exact instant your beam sharpens enough to reveal the Planck length, the energy in your beam becomes so dense that it collapses into a black hole. Your light never comes back. Instead of a picture, you get a hole in space that eats your own beam. The tool becomes the trap. Think of trying to photograph a shy animal with a flash so bright it sets the forest on fire. The only flash strong enough to light the creature is strong enough to burn away the whole scene. You would see nothing but flames where your subject used to be. This is the deepest reason the Planck length hides. To measure it, you must build the very thing that erases it. The act of looking creates a black hole exactly where you wanted to see. Nature has wired the smallest size to the most extreme object, so the two can never be pried apart. Scientists are sure of this logic. It comes straight from combining well-tested rules about light and gravity. It is one of the cleanest arguments in all of physics, and it points to a hard truth. The Planck length is not just hard to see. It may be impossible to see forever by any method built on light. That word forever should give you pause. We are so used to progress, better tools, sharper views, deeper looks. But this wall does not bend to progress. It bends to physics itself. And distance is only half the wall. Because if space has a smallest step, then time may have one too. A shortest possible tick of the cosmic clock. And that tick is so brief it makes a lightning flash look like an ice age. Space has a smallest, meaningful size. So, a natural question follows. Does time have a smallest tick? The answer seems to be yes, and that tick has a name, the Planck time. Here is how to find it. Take the Planck length, the shortest distance that means anything. Now ask how long light, the fastest thing there is, takes to cross that tiny gap. Light is quick beyond belief, so crossing something that small takes a stretch of time almost too short to name. That crossing time is the Planck time. And it may be the shortest slice of time the universe allows. To feel how brief it is, we need comparisons, because the raw number is useless to the human mind. 1 second feels short to you, but inside a single second, the number of Planck ticks is staggering. Try this. Count the seconds since the Big Bang, every second across the entire age of the universe. That is a huge pile of seconds. Close to 14 billion years of them. Now here is the shock. The number of Planck times inside just 1 single second is vastly larger than all the seconds the universe has ever lived. Time, at the bottom, is chopped finer than you could count in 1,000 lifetimes of lifetimes. Another way to hold it, a camera that snaps 1 trillion frames a second, sounds like science fiction, and one almost that fast exists. Yet even that camera, catching light in flight, would need to run for longer than the age of the universe to blink once in Planck time. The gap between our fastest clocks and this tick is a canyon with no bottom. Why would time come in chunks at all? We feel time as a smooth river, always flowing, never skipping. The idea that it might tick in tiny steps, like frames in a movie, feels wrong in the gut. But think about that movie. On screen, motion looks perfectly smooth. A ball flies, a person runs, all fluid and continuous. Get close to the truth though, and the film is just still pictures flashing by, 24 a second. Your eye blends them into flow. Some scientists suspect reality runs the same way, flashing through Planck frames so fast that our lives blur into what feels like unbroken time. Here is where it turns eerie. Below 1 Planck time, the word before may lose its meaning. Asking what happened in half a Planck tick might be like asking what lies north of the North Pole. The question sounds fine, but it points nowhere. Cause and effect, the whole chain of this happened, then that happened, may rest on a floor of Planck ticks with nothing underneath. Scientists hold this idea with care. The Planck time is real as a calculation, easy to write down. Whether time truly comes in hard steps, or whether that is just where our clocks and theories fail, remains unproven. It sits among the great open puzzles. So now we have 2 walls, a smallest distance and a shortest time locked together by the speed of light. Space and time both seem to hit a floor at the same deep level, which forces the strangest question yet. If space has a smallest step, then what is space actually made of? Is it a smooth sheet, like glass? Or is it built from grains, like sand on a beach? The answer splits the world of physics in 2. Run your hand across a table. It feels smooth, solid, one unbroken surface. But you know the secret. That table is a swarm of atoms, mostly empty space. jittering like a crowd, smooth to your skin, grainy to the truth. Now ask the same question about space itself, not the stuff floating in space, but space, the empty stage everything sits on. Is it smooth, like a sheet of glass with no seams? Or is it grainy, built from tiny grains you could never split? This is one of the biggest unanswered questions in all of physics, and the Planck length sits right at the center of it. For centuries, everyone assumed space was smooth, endless, and seamless. You could always zoom in further and find more of the same. This idea runs through the work of Newton, and even through Einstein's grand picture of gravity. Space was a flowing sheet, bending and curving, but never breaking into pieces. Then the quantum world crashed the party. Down at the smallest scales, the quantum rules hint that space might not be smooth at all. It might be woven from tiny threads or tiny grains, each about a Planck length across. Zoom in far enough, this idea says, and the smooth sheet dissolves into a rough weave. There would be a smallest patch of space, a grain you simply cannot cut in half. Picture a beach scene from a plane. The sand looks like a smooth, tan blanket poured across the shore. Land and walk on it, and you feel the grains. Scoop a handful, and each grain is separate, hard, whole. You cannot have half a grain of sand and still call it sand. Maybe space is the same. Smooth from far away, grainy up close, with the Planck length as the size of a single grain. If that is true, it changes everything. A grainy space would mean the universe has a built-in resolution, like the pixels on a screen. There would be a shortest possible move, a smallest possible step. Motion itself might tick from grain to grain instead of gliding, but not everyone buys it. Many scientists still hold that space stays smooth all the way down, and that the Planck length is only where our current theories fail, not where space truly breaks. To them, the graininess is a sign we need better math, not proof of actual grains. Both camps are serious. Both have brilliant minds and hard arguments. This is a live mystery, unsolved right now, argued in real papers by real physicists who disagree. There is even a way we might test it someday. If space is grainy, then light traveling across the universe might get slightly jostled by the grains, like a car feeling every tiny bump in a rough road. Over billions of light years, those bumps could add up to a tiny signal we could catch. So far, the sharpest measurements show space looking smooth down to incredibly fine scales. The grains, if they exist, are hiding well, so the question stands wide open: smooth or grainy, sheet or sand. One of the deepest things we do not yet know about the world we live in. But there is a wilder idea waiting, stranger than smooth and stranger than grainy. Some scientists think that down at this scale, empty space is anything but empty. They think it churns and bubbles and boils, a violent froth hiding beneath the calm. They call it quantum foam. Empty space seems like the most peaceful thing there is. Nothing in it, nothing happening. Just silent, still, endless room. Down at the Planck scale, that picture shatters. A physicist named John Wheeler dreamed up the idea back in the middle of the last century. He suggested that if you could zoom all the way down to the Planck length, empty space would stop looking empty. It would look like a wild, churning froth. He gave it a name that stuck: quantum foam. Here is the idea. The quantum world does not allow true stillness. Even in perfect emptiness, tiny bursts of energy flicker into being and vanish again, faster than any clock could catch. Zoom out, and these flickers blur into smooth, calm nothing. Zoom down to the Planck length, and the flickers dominate. Space seethes. Picture the ocean from an airplane window. From miles up, it looks like a flat blue sheet, calm and glassy. Drop down to the surface in a small boat, and that same ocean is chaos. Waves crash, foam sprays, the water heaves and churns. Space might be just like that, calm and smooth from our giant point of view, boiling and violent at the Planck scale. And this foam is strange beyond waves. In the froth, space itself is thought to twist and pop. Tiny bubbles of space may form and burst. Little tunnels may open and snap shut in less than a Planck time. The very shape of space, its ups and downs and connections, would flicker like static on an old television screen. Even distance and direction get slippery down there. In the foam, the smooth idea of here and there breaks into a boiling mess where the usual rules of geometry blur. Left and right, near and far, all of it trembles. Now feel the size of the gap between that chaos and your calm life. You are sitting still, or so it seems. But the space your body fills is, at the smallest scale, a roaring storm of flickers, bubbles, and tunnels, every instant, everywhere. You never feel it because it happens trillions upon trillions of steps below your senses. The storm is real, but it averages out to the quiet room, you know. Scientists treat quantum foam with care. It is a strong idea that flows naturally from mixing the quantum world with gravity, but no one has ever seen it directly, and no one can, at least not yet. It lives below every microscope we could ever build. So it sits in a special place, more than a wild guess, less than a proven fact. A serious theory waiting for evidence. Some physicists think the foam could do amazing things. They wonder if its tiny tunnels might briefly link far apart places, like secret passages stitched through the froth. Others think the foam holds clues to how the universe began, since the early cosmos was ruled by exactly these Planck-scale storms. The takeaway flips your whole sense of reality. The emptiness around you, the quiet air, the still dark of space, may be the calmest looking part of a hidden inferno. Peace on our scale, chaos at the bottom. And this chaos is not random noise. It follows a deep rule, a law that some call the reason the universe can never fully hold still. A rule that turns the smallest distances into pure uncertainty. Meet the law that makes the foam froth. Why does empty space boil? Why can nothing ever truly sit still? The answer is one of the strangest rules in all of science, and it comes from a young physicist named Werner Heisenberg. His rule is often called the uncertainty principle, and it says something that feels almost unfair. You can never know everything about a tiny thing at once. Pin down where a particle is, and its speed goes fuzzy. Pin down its speed, and its place goes fuzzy. The universe refuses to let you have both, sharp, at the same time. This is not about weak tools or clumsy hands. It is a law woven into reality. The more you nail one fact, the more the other slips away, like squeezing a water balloon and watching it bulge out somewhere else. For everyday life, this rule hides. You can know where your car is and how fast it moves. No problem, because a car is huge compared to a particle. The fuzziness is there, but it is so small you would never notice. Shrink down to the tiny world, though, and the fuzziness takes over. It runs the show. Now bring this rule down to the Planck length, and it turns wild. At that size, you are trying to know a position with insane precision. You want to say a particle sits exactly here, in a spot smaller than anything imaginable. But the uncertainty rule fights back hard. Pin a position that tightly, and the particle's energy goes wildly uncertain. It could suddenly carry a huge, unpredictable burst of energy, flaring up from nothing. And you already know what huge energy in a tiny space does. It bends space. It threatens to collapse into a black hole. So the tighter you try to pin a spot at the Planck scale, the more violent and unpredictable the energy there becomes. Certainty itself breaks down. This is the engine behind quantum foam, because you can never say a region has exactly zero energy. Empty space is forced to flicker. Tiny bursts pop up and die, on and on, because the rule forbids perfect, boring stillness. Emptiness churns, because the universe will not allow it to be perfectly known. Picture trying to hold a bar of wet soap. Squeeze gently, and it sits in your palm. Squeeze harder to control it better, and it shoots out of your grip. The tighter you clamp down, the more it escapes. At the Planck scale, position and energy play the same game. Grip one hard, and the other bursts free. Scientists have tested the uncertainty rule countless times, in countless ways. It holds every single time. It is one of the most solid, confirmed facts in all of physics. What it means down at the Planck length is where things turn speculative, because we cannot go there and check. But the rule itself is rock solid, so here is the picture we have built. Space and time have a smallest step. At that step, emptiness boils with quantum foam, and the foam boils because a deep law forbids the universe from ever holding perfectly still. Every path down to the Planck length runs into the same wall of extreme energy, which raises a blunt question. Just how much energy would it really take to reach this scale? The answer is a number so vast it dwarfs stars. Let us try to hold it. We keep saying it takes enormous energy to reach the Planck scale. Now let us feel just how enormous, because the truth is almost funny in how far beyond reach it sits. To probe a distance, you need a particle with energy matched to that distance. Small distance, big energy. To reach the Planck length, you need a single particle carrying an amount of energy that belongs to explosions, not to specks. Here is a comparison to start. A single mosquito in flight carries a certain tiny amount of energy. It is nothing to you, a soft bump against your arm. Now imagine cramming all of a flying mosquito's energy into one particle, one point far smaller than an atom. That is roughly the energy scale we are talking about, packed into a spot unimaginably tiny. That might not sound scary at first. A mosquito? But the horror is in the packing. Spreading a mosquito's energy across a mosquito is gentle. Squeezing that same energy into a single subatomic particle is like squeezing an entire thunderstorm into a grain of salt. The concentration is what breaks the world. Now think about where that energy would have to come from. Our machines fling particles at incredible speeds and slam them together. The biggest one ever built pushes particles to nearly the speed of light and crashes them in a tunnel miles around. It reaches energies that let us glimpse deep inside the atom. Yet even that giant machine falls short of the Planck scale by a factor so large it defies picturing. To reach the Planck energy with a machine built like ours, you would need one far, far bigger. How big? By some honest estimates, a particle collider large enough would have to be about the size of an entire galaxy, a ring of magnets stretching across millions of stars. Sit with that. Not a bigger building, not a bigger country, a machine the size of the Milky Way, just to touch the bottom of the small. There is another way to picture the energy. If you could gather all the power the sun pours out in a stretch of time and focus it perfectly onto one tiny particle, you would start to approach the neighborhood we mean. The energies of the Planck scale are the energies of the early universe, of cosmic birth, not of any lab a civilization could hope to build. This is why scientists are honest and humble here. They can calculate the Planck energy exactly. They know the number, but reaching it is another matter entirely. It may sit forever beyond any technology, not because we are not clever, but because the scale itself belongs to the extremes of creation. And this changes how we chase the mystery. We cannot build a machine to visit the Planck length directly. So instead, scientists look for tiny hints, faint echoes, places where the Planck scale might leave a fingerprint on things we can measure, like ancient light or the flicker of distant stars. The direct door is shut, maybe forever. We are left knocking, listening for whispers through the wall. To feel how far short we truly fall, it helps to look at our best machines, the mightiest tools humanity has ever built. Because even at their most powerful, they leave us stranded a staggering distance from the goal. Let us see just how big that gap really is. Deep under the border of France and Switzerland runs a tunnel, a ring about 17 miles around. Inside it, humanity built the most powerful particle machine in history. Scientists use it to smash particles together and peer into the guts of matter. This machine is a marvel. It speeds particles up until they move a hair below the speed of light, whipping around the ring more than 10,000 times every second. Then it crashes them head-on, releasing bursts of energy that recreate conditions from the first moments after the Big Bang. With it, Scientists found long-hunted pieces of the atom and confirmed ideas that took decades to test. If any tool on Earth could get us close to the Planck scale, it would be this one. It does not even come near. Let us measure the gap honestly. This great machine can probe distances down to a certain tiny size, far smaller than a proton. That alone is a triumph, a view into a world no eye will ever see. But the Planck length is smaller than what this machine can reach by a factor of about 10,000 trillion. Try to picture that gap. Say the machine's reach with a width of one step you take walking. Then the Planck length, on that same scale, would be smaller than the width of a single atom under your shoe. The distance we can probe and the distance we want to probe are separated by a canyon that dwarfs the machine itself. Here is another way to feel it. Suppose you built a ladder from the size this machine can see all the way down to the Planck length, and each rung shrank the distance by 10 times. You would need about 16 rungs. That sounds small until you remember what each rung costs. Every single step down demands vastly more energy than the step before. The machine we have already strains a whole continent's cleverness to reach its rung. 16 more rungs down is a climb no imaginable machine can make. Think of it like eyesight. Your bare eyes see a certain amount of detail. A good microscope multiplies that enormously, revealing cells and even hints of atoms. That leap feels almost magic. Now imagine needing a jump that same size, done over and over, more than a dozen times in a row, each one harder than the last. The Planck length hides at the end of that impossible staircase. Scientists are clear-eyed about this. Our machines are the pride of human science, and they have taught us wonders. But they were never going to reach the Planck floor. The energies required belong to a different realm, the realm of cosmic birth. No collider we could fund or build closes that gap. This is not a sad story, though. It is a challenge that pushes science sideways instead of straight ahead. If we cannot smash our way down to the Planck length, maybe the universe already ran the experiment for us. The Big Bang itself reached those energies. Its echoes still ripple through the sky. So, scientists turn their eyes upward, hunting for Planck-scale secrets written in starlight and in the faint afterglow of creation. But before we chase those echoes, we have to face the deepest trouble of all. Because at the Planck length, our two greatest theories, the ones that have never failed us, both crack apart. And they crack in ways that leave physicists staring at a blank page. Let us meet the first crack. Physics rests on two giant pillars, two grand theories, each a triumph, each tested 1,000 times, and never once caught wrong in its own domain. At the Planck length, both crack. Let us start with the first. The first pillar is Einstein's theory of gravity, his masterpiece about space and time. It gave us a stunning idea. Gravity is not a force reaching across empty space. Gravity is the bending of space and time by mass. A heavy object, like the sun, sinks into the fabric of space and warps it, and everything nearby rolls along the curves. Picture a bowling ball on a stretched rubber sheet. The ball sinks in and makes a dip. Roll a marble nearby, and it curves toward the ball, caught in the slope. Planets circle the sun for the same reason. They are rolling along the dip the sun carves into space. This idea has passed every test. It predicted bending starlight, wobbling orbits, and ripples in space from crashing black holes. It works beautifully, but it has a hidden weakness. Einstein's theory assumes space is smooth, perfectly smooth, a seamless sheet you can always divide into finer pieces. The whole idea rests on gentle curves flowing without a break. It is a theory of the large and the smooth, the theory of planets, stars, and galaxies. Now shrink down toward the Planck length, and the smoothness dies. Down there, quantum foam churns, space bubbles and pops, distance flickers. An Einstein's smooth sheet cannot survive in a place like that. His equations demand a calm, flowing surface, and the Planck scale offers a raging storm. Feed the storm into his math, and the answers blow up. They spit out infinity, a sign the theory has hit its limit and given up. Infinity is the alarm bell of physics. When a theory answers a real question with infinity, it is telling you it no longer knows what it is talking about. And that is exactly what Einstein's gravity does at the Planck length. Ask it what space and time do down there, and it screams nonsense. Think of a beautiful map of a country, perfect for planning a road trip across states. It shows highways, cities, rivers, all with gorgeous accuracy. Now try to use that same map to find a single grain of sand on one beach. The map is useless at that scale. It was never built for it. Einstein's gravity is that map, flawless for the cosmos, blind at the Planck flaw. Scientists are certain about this failure. It is not a maybe. Gravity's greatest theory truly breaks at the Planck scale, and physicists have known it for a long time. The theory itself points to its own edge, like a note that says the map ends here. This is a big deal, and here is why. Gravity rules the biggest things, stars and galaxies, and the shape of the whole universe. If it fails at the smallest scale, then we do not actually understand the universe at its deepest level. There is a hole in our knowledge, right at the bottom of reality, and gravity is only one pillar. You might hope the other pillar, the theory of the very small, would ride to the rescue and explain what happens down there. It does not, because at the exact same wall, for its own reasons, quantum mechanics breaks too. The second great pillar of physics is quantum mechanics, the theory of the very small. It rules atoms, particles, and light, and it is astonishingly good. It powers the phone in your pocket, the lasers in stores, the chips in every computer. Its predictions match reality to a precision that borders on the absurd. Quantum mechanics is the master of the tiny, so surely, you might think, it will handle the Planck length with ease. That is its home turf, the world of the small. It fails there too, and the reason is beautiful and cruel. Quantum mechanics has its own hidden assumption, the mirror image of gravities. Gravity assumes space is smooth. Quantum mechanics assumes gravity is weak enough to ignore. In the tiny world, gravity between two particles is so absurdly faint that quantum physics simply leaves it out. And for almost everything, that is fine. The pull of gravity between two electrons is laughably small next to the other forces at play. Picture two feathers floating near each other. Yes, they pull on each other with gravity, but the pull is so tiny it means nothing. A breath of air, a speck of static, anything overwhelms it. Quantum mechanics treats the particle world the same way. Gravity is there, but it is a whisper lost in a hurricane, safe to ignore. At the Planck length, that whisper becomes a roar. Down at this scale, you are packing energy into a spot so small that gravity is no longer weak. Remember, energy bends space, and at the Planck length, the energies are so concentrated that gravity grows as strong as every other force. The whisper quantum mechanics ignored has turned into a scream it cannot drown out. So now quantum mechanics faces a monster it was never built to fight. Its equations have no proper place for strong gravity. They assumed they would never need one. Force strong gravity into quantum math, and it too breaks down, coughing out nonsense and infinities. The same alarm bell we heard from Einstein's side. Here is the trap laid bare. Gravity's theory works for the big and smooth, and dies when things get small and rough. Quantum theory works for the small and weak gravity, and dies when gravity gets strong. The Planck length is the one place in the universe that is both small and strongly gravitational at once. It is small enough to need quantum rules, and dense enough to need gravity rules, both at full strength, in the same spot, at the same time. Neither theory can handle that. Each one was built to ignore exactly the thing the other one needs. So, at the Planck length, both go blind together. Scientists are certain of this double failure. It is one of the clearest and most famous gaps in all of physics. Our two best descriptions of reality, both nearly perfect in their own worlds, both fall silent at the same tiny wall, and they leave us with no working picture of what space and time truly do down there. This is more than a puzzle. It is a signal. When two great theories both break at the same place, physicists smell something deeper hiding underneath, a missing theory, a truth we have not found yet. So the Planck length is more than a wall. It is a battlefield, where our two greatest ideas about reality wage a war neither can win. Let us step onto that battlefield. Two theories, both brilliant, both proven, both broken at the same tiny wall. And here is the part that keeps physicists awake. The two theories do not just fail separately, they contradict each other. They cannot both be the final truth, because they describe reality in ways that clash head-on. This is the great war of modern physics, and the Planck length is the battlefield where it plays out. Einstein's gravity paints reality as smooth and steady. Space and time flow in gentle curves. Given the exact setup, the theory tells you exactly what happens next. The universe, in this view, is orderly and precise, a grand clockwork of bending space. Quantum mechanics paints reality as jittery and uncertain. Nothing is exact. Everything is a blur of chance, a swarm of maybes. A particle does not have one clear path. It explores many at once, and only settles when you look. The universe, in this view, gambles at every step, smooth and certain against jittery and random. These are two opposite pictures of what reality is made of. For most of the universe, the clash stays hidden. Gravity rules the big stuff, quantum rules the small stuff, and they politely stay out of each other's way. Planets do not care about quantum blur. Atoms do not care about gravity's curves. Peace holds because they never truly meet. At the Planck length, they are forced to meet, and they cannot agree. Picture two brilliant experts who each explain the world perfectly in their own field, but whose core beliefs flatly contradict. One insists reality is a smooth, predictable machine. The other insists reality is a fuzzy roll of the dice. Put them in one room and force them to describe a single thing together, and they end up shouting past each other. That single thing is the Planck length, and the shouting is the infinities in the math. So physicists face a hard truth. At least one of these theories must be incomplete, maybe both. There has to be a deeper theory underneath, one that contains both gravity and the quantum, and that tells us what really happens at the Planck scale. Scientists call this missing masterpiece a theory of quantum gravity. Finding it is one of the biggest quests in all of science. Many of the greatest minds of the last century chased it and came up short. Einstein himself spent his final decades hunting a grand, unified picture and never found it. The problem is that fierce. The two theories resist joining like magnets shoved wrong end to wrong end, yet the search has not been empty. Out of this war, bold new ideas have risen, each one trying to be the peace treaty. Each one tries to describe space and time at the Planck length in a way that does not break. Some picture space as a weave of tiny loops. Some picture reality as vibrating strings. Some suggest our whole world is a kind of projection from a distant surface. None is proven. All are serious. And each one paints a picture of the Planck scale stranger than the last. Scientists are honest about where we stand. The war is real and unresolved. We do not yet have the winning theory. What we have are daring guesses, tested where we can test them, waiting for the day nature tips its hand. So let us walk through these guesses, one by one. And the first one imagines that space itself is knitted, like a sweater, from unbreakable loops. The first bold attempt to tame the Planck scale is called loop quantum gravity, and its central idea is stunning in its simplicity. Space is not a smooth backdrop. Space is woven, like fabric, from tiny loops. Here is the picture. Zoom in on empty space, down and down toward the Planck length. In this theory, you would eventually reach the threads, tiny loops of something, linked together into a vast web. That web is space. There is no smooth sheet underneath. The web is the bottom. Think of a sweater. From across a room, it looks like a single smooth piece of cloth. Bring it to your eyes, and you see it is knit from yarn, loop after loop after loop, all linked. There is no smooth cloth hiding between the loops. The loops are the sweater. Loop quantum gravity says space works the same way. Smooth from far off, made of tiny linked loops up close. And these loops have a size, about the Planck length. That means space itself has a smallest possible chunk. You cannot have half a loop of space, the same way you cannot have half a stitch and still call it a stitch. The theory predicts a real, hard bottom to smallness, a grain of space you can never cut. This solves a nasty problem. Remember how the old theories spit out infinities when things got too small? Those infinities came from letting distances shrink forever, all the way to zero. But if space is made of loops with a smallest size, distances cannot shrink to zero. They stop at one loop, the bottom is built in, and when there is no zero to fall into, the dreaded infinities never appear. The math stays clean. The theory paints a strange new picture of the void. Empty space becomes a buzzing network of loops, constantly shifting, linking and relinking. Area and volume come in tiny fixed chunks, like money that only comes in whole coins with no way to split them finer. You can have one coin or 2 coins of space, never 1.5. Even time might come in loops in this view. The smooth flow you feel could be a rapid tick through Planck-sized steps, one loop of time after another, blurred into the river we call now. Loop quantum gravity even dares to peak before the Big Bang. In the normal story, the universe starts from a single point of infinite crush, a place where all math dies. But loops refuse to let anything shrink to a true point, so some versions of this theory suggest the universe never had that impossible starting point. Instead, an older universe collapsed, squeezed down to the smallest loops, and bounced back out as our Big Bang. A cosmic rebound instead of a birth from nothing. Scientists are careful with all of this. Loop quantum gravity is a serious, respected theory, built by careful minds with hard math. But it is not proven. No experiment has confirmed the loops, because we cannot see the Planck scale directly. It stands as a strong candidate, one possible answer, waiting for evidence that may take generations to find. It is a beautiful vision, a universe knitted from tiny loops, with no true smoothness and no true zero at its heart. But it is not the only vision. A rival idea sweeps the loops aside and offers something even stranger. It says the smallest things in reality are not loops at all, but tiny strings, plucked and humming like the strings of a guitar. The second great attempt to conquer the Planck scale is famous even outside of science. You may have heard its name, string theory, and its central idea is as musical as it is mind-bending. Here is the claim: the smallest bits of matter are not tiny dots. They are tiny strings, unthinkably small loops and lines of vibrating energy, each about a Planck length long. Everything you have ever seen, every particle, every speck of light, is one of these strings, humming. And here is the beautiful part. The strings can vibrate in different ways, like the strings of a guitar. Pluck a guitar string one way and you get a low note. Pluck it another way and you get a high note. Same string, different song. String theory says the particles of nature work the same way. One vibration gives you an electron. Another vibration gives you a particle of light. Another gives you a quark. All the same kind of string, just playing different notes. Sit with how gorgeous that is. In this view, the whole universe is a symphony. Every particle is a note. Matter, light, and force are all music played on strings smaller than anything we can ever hope to see. Reality becomes a song, and the Planck length sets the size of the instrument. String theory was not built to be pretty, though. It was built to solve the war, and it seems to pull off something the old theories could not. It naturally includes gravity. When physicists worked out the notes a string could play, one of the vibrations turned out to describe the particle of gravity itself. Gravity fell out of the math on its own. Uninvited. Welcome. For a theory trying to join gravity and the quantum, that was a thrilling sign. The strings also tame the infinities. A dot has zero size, and zero size is where the old math exploded. But a string is not a dot. It has a length, about the Planck length. That tiny size smooths out the worst of the crashes, the way a rounded edge is gentler than a razor point. The infinities that plagued the old theories soften and fade. But string theory asks for something wild in return. For the music to work, the universe needs more dimensions than we see, not just the three of space and one of time that we know, but several extra ones, curled up so small we never notice them. Picture a garden hose from far away. It looks like a thin line, one dimension. Walk up close, and you see it is a tube with a hidden dimension wrapped around it that you missed from a distance. String theory says our universe hides extra dimensions the same way, curled down near the Planck length, tucked out of sight. Scientists hold string theory with both hope and doubt. It is elegant, powerful, and has taught us deep math and deep ideas, but it has never been tested. Its strings and hidden dimensions live at the Planck scale, far below any machine. Some physicists love it and have spent their lives on it. Others worry it can never be checked, and so can never be proven. The debate is real and sharp, so we have two grand visions, space woven from loops, reality strummed on strings. Both try to describe the Planck flaw, and both stay unproven, and they share a haunting hint. In both, the smallest scale has a hard bottom, which pushes us toward an idea that sounds like science fiction. What if reality is built from pixels, like the screen you are looking at right now? Look closely at any screen, your phone, your television, a billboard. Get close enough, and the smooth image breaks into tiny squares, pixels, each one a single dot of color. There is no picture hiding inside a pixel. It is the smallest piece the screen can show, a hard, built-in bottom to detail. Now, here is a thought that has crept into serious physics. What if reality has pixels too? We have been circling this idea, and now let us face it head-on. Both loop quantum gravity and string theory hint at a smallest possible size, the Planck length. If space truly has a smallest chunk, then the universe might work like a screen. There would be a finest possible detail, a bottom resolution, below which reality simply has nothing more to show. Think about what that means for motion. On a screen, a moving dot does not glide smoothly. It jumps from pixel to pixel, so fast, your eye blends the jumps into smooth motion. If space is pixelated at the Planck length, then everything that moves, including you, might really be jumping from one tiny patch of space to the next. Planck step by Planck step, the smoothness you feel would be a beautiful illusion. Like the smooth motion on a screen, time might pixelate too. We met the Planck time, the shortest tick. Put a smallest length and a shortest time together, and you get a universe that updates in tiny frames, like a video playing at an unthinkable speed. Reality as the ultimate high-definition movie, with the Planck scale setting both the pixel size and the frame rate. This idea carries a strange comfort and a strange chill at once. The comfort is that pixels solve the infinities. A screen never has to show infinite detail, so it never crashes trying. A pixelated universe never has to deal with true zero distance, so its math stays clean. The chill is what it whispers about the nature of reality. A pixelated world sounds a lot like a made thing, a screen, a display, maybe even a simulation, though we will save that unsettling road for later. Here is a comparison to hold it. Imagine a photo printed at low resolution. From across the room, it looks perfect. Lean in close and you hit the blocky squares. You cannot zoom past them. There is no more detail to find, because the picture has a bottom. The Planck length might be the universe's version of that bottom. Zoom in on reality, and eventually you hit the blocks, with nothing finer underneath. Scientists are cautious and split on this. Some think space really is grainy or pixel-like at the Planck scale, and they hunt for signs of it in distant light. Others think reality stays smooth all the way down, and that the pixel picture is just a handy image, not the literal truth. The measurements so far show space looking remarkably smooth, so if there are pixels, they hide extremely well. This stays an open question, argued in real labs. But the pixel idea opens a door to something even wilder, because if the universe has a smallest resolution, some physicists wonder where all the detail is stored. And one shocking answer says the information that builds our three-dimensional world might actually be painted on a flat, distant surface. Your whole reality, a projection. Let us step into the hologram. Get ready, because this next idea is one of the strangest in all of physics, and serious scientists take it seriously. It is called the holographic principle, and it suggests that our three-dimensional world might really be a kind of projection painted on a faraway two-dimensional surface. Start with a regular hologram, the shiny image on a credit card that seems to float in 3 dimensions. Tilt it, and the image shifts, like a real object with depth, but the hologram itself is flat. All the information needed to build that 3D image is stored on a flat surface. Depth from flatness. A rich world encoded on a thin sheet. The holographic principle says the universe might work the same way. All the information about everything inside a chunk of space, every particle, every event, might be fully encoded on the flat boundary around that chunk. The inside, with all its depth, would be like the floating image. The real storage would sit on the surface. Where did such a wild idea come from? It came from black holes, and it came from the Planck length. Scientists studying black holes made a shocking discovery. The amount of information a black hole can hold does not depend on its volume, the space inside it. It depends on its surface area, the size of its outer edge. And that surface is measured in tiny Planck-sized patches, each one holding a single bit of information, like a pixel holding one dot of the picture. Read that again, because it defies common sense. You would expect a big 3-dimensional region to store information based on how much room is inside it, its volume. But black holes store it based on their surface, their skin. It is as if all the stuff inside is really written on the outside wall, and the writing is done in Planck-sized letters. Picture a library. You would think the number of books it can hold depends on the volume of the building, all that inside space. Now imagine learning that it actually depends only on the area of the walls, as if every book were somehow written on the surface of the room, not stored within it. That is the jolt the holographic principle delivers about our universe. Physicists took this black hole clue and made a daring leap. Maybe all of reality is like this. Maybe the 3-dimensional world we live in is the floating image, and the true information lives on a distant 2-dimensional boundary, written in Planck-scale pixels. Our depth, our sense of inside and volume, would be the hologram, real to us but projected from a flatter truth. This idea has grown into one of the most powerful tools in modern physics. In certain worked-out cases, scientists have shown that a hard problem about gravity inside a space can be solved by looking at a simpler description on its boundary. The two descriptions, inside and surface, turn out to be secretly the same. That success is real math, checked and rechecked, and it stunned the field. Scientists remain careful about how far it goes. The holographic principle works beautifully in certain model universes. Whether our actual universe is fully holographic stays unproven, an active and thrilling area of research, but the black hole clue that started it all is solid, and it points straight at the Planck length as the size of reality's smallest pixel of information. And that raises a question we keep dancing around. If the smallest length is this strange, then what does the word distance even mean once you shrink below it? The answer may be that it means nothing at all. We throw the word distance around all day. How far to school? How far across the room? How far to the moon? Distance feels like the most solid, obvious thing in the world. You measure it, you cross it, you know it. At the Planck length, distance may stop meaning anything. We have circled this idea, and now let us face it fully. All our talk of distance assumes something simple, that between any 2 points, no matter how close, there is always a smaller distance, halfway, a quarter of the way, an eighth, forever. Distance, we assume, can always be sliced finer. The Planck length breaks that assumption. If it truly is the smallest meaningful size, then below it, the idea of a smaller distance falls apart. Ask how far apart 2 points are when they sit less than a Planck length from each other, and the question may have no answer. Not a hard answer. No answer. The words point in a direction where reality has nothing to say. Here is why. To have a distance between 2 points, you need to be able to tell them apart. You need to know that one is here and the other is over there. But at the Planck scale, quantum foam churns, positions blur, and any attempt to pin 2 points that close collapses into a black hole. The 2 points smear together into a single fuzzy mess. There is no clean here and there anymore. And with no here and there is no between. And with no between, there is no distance. Think of 2 dots drawn on a balloon with a marker. Blow the balloon up, and the dots are clearly separate, with space between them. Now let the balloon shrink, and the dots come closer, closer, until the ink bleeds together into one blob. At some point, you cannot say there are 2 dots at all. There is just one smear. Below the Planck length, space does something like that to any 2 points. They lose their separateness. They become one. This flips a lifetime of intuition. We are taught that space is infinitely divisible, that you can always zoom in more. The Planck length says the zoom has a limit, and past that limit, the very concept of separation dissolves. Distance is not just hard to measure down there. It may simply cease to be a meaningful thing. Some physicists put it starkly. Asking what the distance is below the Planck length might be like asking what is north of the North Pole. The words fit together grammatically. The question sounds fine, but it points to a place that does not exist. North runs out at the pole. Distance may run out at the Planck length. Scientists hold this carefully. That distance loses meaning below the Planck scale is a strong and widely respected idea, flowing from combining gravity and the quantum. But since we cannot go there and check, it lives in the land of well-reasoned theory rather than tested fact. Still, it reshapes how we think about space at its deepest level. So we reach a dizzying place. The smallest distance may be the last distance. Below it, the ruler, the ideas, and the words all give out. And this is where reality gets truly bizarre. Because at this scale, the trap we keep meeting, energy collapsing into black holes, does not stay a threat. It becomes real. Tiny black holes may actually flicker in and out of existence, right there in the foam, faster than any clock. Let us watch them appear. We have talked about black holes as a threat, a trap that springs whenever too much energy crowds into too small a space. At the Planck scale, that threat stops being just a warning. It may come true, over and over, in the churning foam of empty space. Scientists think tiny black holes may flicker into being at the Planck length, everywhere, all the time. Not the giant black holes born from dying stars. These would be the smallest black holes possible, each about a Planck length across, blinking into existence and vanishing again faster than thought. Here is how it could happen. Remember the uncertainty rule, the one that forbids empty space from ever holding still. It lets little bursts of energy flash up out of nothing for the briefest instant. Usually these bursts are gentle and fade away harmlessly. But at the Planck scale, a burst can carry so much energy in so small a spot that it does what concentrated energy always does. It bends space around itself into a black hole. So in the quantum foam, tiny black holes are thought to pop up constantly. They form from a flicker of borrowed energy, exist for less than a Planck time, and then vanish, giving the energy back. The foam is not just bubbling space. It may be a sea of micro black holes, winking on and off trillions upon trillions of times in every tiny patch, every instant. Picture a pot of water at a rolling boil. Bubbles form on the bottom, rise, and pop, appearing and vanishing in a churning dance. Now, shrink that image down past all imagining to the Planck scale and swap the bubbles for tiny black holes. That is one picture of what empty space might be doing at its deepest level, a boiling broth of the most extreme objects in the universe, each one smaller than small, flashing in and out. Feel how strange this is. Black holes, in our everyday picture, are cosmic monsters. They eat stars. They anchor galaxies. They are the heavyweights of the universe. And yet, the same physics suggests the tiniest versions of these monsters may fill the emptiness around you. Right now, in the space between your fingers, born and dead in less time than light needs to cross a single atom's core, these micro-black holes would be nothing like their giant cousins in one key way. A giant black hole is stable and long-lived, ruling its corner of space for ages. A Planck-sized black hole would be the opposite, wildly unstable, gone almost the instant it forms. It could not last. The rules that let it appear also demand it disappear at once. Scientists treat these tiny black holes as a strong theoretical possibility, not a confirmed sighting. They flow naturally from mixing gravity with quantum uncertainty, which is exactly the mix that rules the Planck scale. But no one has ever detected one, and they may be forever beyond reach. So they sit as a serious idea about what the bottom of reality is truly like. And this raises an obvious question. If these tiny black holes appear, why do they vanish so fast? Why can they not stick around like the giant ones? The answer comes from a discovery that shocked the world of physics. The realization that black holes are not truly black at all. They glow, they leak, and the smaller they are, the faster they die. Let us find out why. For a long time, everyone thought black holes were perfect traps. Whatever fell in, stayed in. Nothing escaped, not even light. That is where the name comes from. Black, because no light comes out. A one-way door to nowhere. Then a physicist named Stephen Hawking changed the picture forever. He discovered that black holes are not perfectly black. They glow, ever so faintly. They leak energy into space, and over unimaginable stretches of time, they slowly shrink and die. This leaking has a name. It is often called Hawking radiation, and understanding it explains why the tiny Planck-scale black holes vanish almost the instant they appear. Here is the idea, kept simple. Remember that empty space bubbles with pairs of particles flickering in and out. Normally, a pair pops up and instantly cancels back to nothing. But right at the edge of a black hole, something can go wrong for the black hole. One member of the pair falls in, and the other escapes, flying off into space as real radiation. The black hole just leaked a tiny bit of energy. Do this endlessly, and the black hole slowly bleeds away. Now, here is the crucial twist, the one that dooms the tiny black holes. The smaller a black hole is, the faster it leaks. Small black holes glow hotter and bleed quicker. Big black holes leak so slowly, it takes longer than the age of the universe to matter. But shrink a black hole down, and the leaking speeds up ferociously. The tiniest black holes evaporate almost instantly, dumping all their energy in a final flash. Picture a puddle of water. A wide, shallow puddle, spread across a parking lot, dries slowly over a whole day. But a single drop of water on a hot stove hisses and vanishes in a heartbeat. Same water, wildly different speeds, all because of size and concentration. Black holes evaporate the same way. Big ones linger for eras. Tiny ones flash and are gone. A Planck-sized black hole is the smallest of all, so it evaporates the fastest of all, in about 1 Planck time, the shortest tick there is. It forms from a flicker of foam and evaporates in a flash, its whole life shorter than the time light takes to cross a single proton. Blink, and you would miss it by an amount of time beyond counting. This is why the quantum foam can boil with micro-black holes without filling the universe with them. They cannot last. Each one appears and evaporates almost at once, its energy returned to the froth. The foam stays a churning balance of black holes being born and black holes dying, all at the deepest scale of reality. Scientists hold Hawking radiation in high regard. It flows from solid physics, blending the quantum world with black holes, and most physicists accept it as very likely real. even though the faint glow of a real black hole is far too weak for us to detect. The behavior of Planck scale black holes takes this idea to its extreme edge, into territory we cannot yet test. But the core insight that black holes glow and that small ones die fast stands as a landmark of modern science. So the Planck scale gives us space that boils with tiny black holes, each flashing into being and evaporating in the shortest possible instant. It sounds like the most extreme place imaginable, and here is the twist that should raise the hair on your neck. The entire universe was once exactly this small. Everything that exists, squeezed down to a single Planck length. Let us travel back to that moment. Everything we have explored lives at the smallest scale, hidden far below our senses. Now brace yourself for a turn that changes the whole story. There was a moment when the entire universe, every particle that would ever exist, was squeezed down to around the Planck length. Rewind the cosmos. Right now, the universe is unthinkably vast, billions of light years across, filled with galaxies beyond counting. But it is expanding. Everything is drifting apart. So run the film backward, and everything rushes together. Galaxies pull in, space shrinks. The whole universe grows smaller and smaller as you wind the clock back toward the beginning. Keep rewinding, all the way to the very first instant, and the entire universe collapses down to a single, staggeringly tiny point. And the size of that point, at the earliest moment we can even talk about, was close to the Planck length. Sit with the scale of that. Every star you have ever seen, every galaxy in every telescope image, all the matter and energy that would ever become planets and people and oceans and light. All of it, packed into a space smaller than a single subatomic particle, smaller than anything. The whole cosmos, Planck-sized. The everyday mind rebels at this. How can everything fit into almost nothing? But that is exactly what our best understanding says. The early universe was not empty and waiting to be filled. It was small and impossibly dense, holding all its future within a speck at the bottom of smallness. Picture the largest thing you can imagine, then squeeze it into the smallest thing you can imagine, and you still fall hopelessly short of this. The entire observable universe, crushed down past atoms, past their tiny cores, down to the Planck scale. There is no comparison in daily life that reaches it. It stands alone as the most extreme condition reality has ever known. And this is why the Planck length matters so deeply. Beyond being a curiosity of the small, the Planck scale is where the universe began. To understand the first instant of creation, you have to understand what happens at this size. The birth of everything played out on the smallest stage there is. But here is the humbling part. Remember that at the Planck length, both our great theories break. Gravity's theory dies. Quantum theory dies. Neither can describe what happens there, which means neither can describe the very first moment of the universe. Our best science, pushed back to the beginning, hits the same wall we have met all along and falls silent. So the origin of everything sits locked behind the Planck barrier. We can rewind the universe with confidence, almost all the way back. We can trace the story through the growth of galaxies, the forging of atoms, the first light. But at the final step, the moment when the whole cosmos was Planck-sized, our theories give out. The first instant hides behind the very wall we have been exploring. Scientists are honest about this frontier, that the early universe was once incredibly small and dense, is well supported by strong evidence, from the expansion we see to the faint afterglow of the beginning. What happened at the exact Planck-sized instant remains beyond current theory, one of the deepest unknowns in all of science. This first sliver of time even has a name. Physicists call it the Planck epoch, and it is the one chapter of the universe's story that no theory can yet read. Let us stare into that unwritten page. Every story has a beginning, and the universe is no different. But the very first chapter of the universe's story is one that no scientist can yet read. It has a name, the Planck epoch, and it may be the single most mysterious slice of time that has ever existed. Here is what the Planck epoch is. Take the moment of the Big Bang, the start of everything, as time 0. Now count forward the tiniest possible amount, 1 Planck time, the shortest tick there is. That first, unthinkably brief sliver, from the very start up to 1 Planck time, is the Planck epoch, and it is a complete blank in our understanding. During this epoch, the whole universe was around the Planck length in size, and impossibly hot and dense. All 4 of nature's forces, the ones that today are separate and distinct, are thought to have been merged into a single unified force. The universe was a smooth, blazing whole before it split into the varied cosmos we know. It was reality in its rawest, most primal state, and we cannot describe it, not with gravity's theory, which breaks at the Planck scale, not with quantum theory, which breaks there too. The Planck epoch is the exact moment when everything was both as small and as strongly gravitational as it gets, the one place where both our theories fail at once. So this first flicker of time is a locked room, and we do not have the key. Think of a book with a beautiful, detailed story, except the very first page is torn out. You can read everything after it. You can piece together the plot, follow the characters, understand how it all unfolds. But that first page, the one that would tell you how it truly began, is missing. The Planck epoch is that torn-out first page of the universe. What makes it so tantalizing is that everything came from it. The seeds of every galaxy, the balance of matter, the very laws that would shape all of time, may have been set in that first sliver. Get that page back, and we might understand why the universe is the way it is at the deepest possible level, why there is something rather than nothing, why the cosmos took the shape it did. Scientists have not given up on it. The great hope is that a working theory of quantum gravity, the missing masterpiece that joins gravity and the quantum, would finally let us read the Planck epoch. The loop theories and string theories we met are all, in part, attempts to recover that lost first page. If one of them proves true, we might finally glimpse the birth of everything. For now, honesty rules. Scientists are confident the Planck epoch happened because the universe clearly has a beginning and clearly expanded from a tiny, hot state. What went on during that first sliver stays unknown, a frontier no experiment has touched and no theory has conquered. It sits at the outer edge of human knowledge, waiting, so the smallest scale in the universe turns out to guard its greatest secret. The Planck length is where reality began and where our understanding ends. And this loops us back to a question that has been quietly building this whole time, a question that sounds simple but cuts to the bone. Can anything ever be smaller than the Planck length? Or is that question itself empty, a door that opens onto nothing? We have called the Planck length the smallest meaningful size. We have watched rulers collapse, distances dissolve, and theories fail below it. So now let us ask the question straight out. Can anything actually be smaller than the Planck length? The honest answer splits into 2 very different possibilities, and scientists genuinely disagree about which is true. The first possibility is bold. Nothing can ever be smaller. The Planck length is a hard, absolute flaw, the smallest real size in the universe, full stop. In this view, space comes in tiny chunks, like the loops or pixels we met, and there is simply no such thing as a smaller distance. Asking for something tinier is like asking for a whole number smaller than 1 when counting apples. It does not exist. The flaw is real and final. The second possibility is subtler. Maybe smaller sizes could exist in principle, but we can never measure them, never reach them, never make them matter. In this view, the Planck length is not necessarily the smallest thing that could be, but it is the smallest thing that can ever mean anything to us or to physics. Below it, even if something is there, it is forever sealed away, unmeasurable and untouchable. So it makes no difference to reality as we can ever know it. Notice how close these two come in practice. Whether the Planck length is truly the bottom or just the bottom of what can ever be known, the result for us is the same. Nothing smaller can be seen, built, measured, or used. The door is shut either way. The debate is about what lies behind a door that can never be opened. Here is a way to feel the strangeness. Imagine asking for a color darker than perfect black. In everyday terms, black is as dark as it gets. You can say the words darker than black, and they sound fine, but they point nowhere. There is no such color to find. Some scientists think smaller than the Planck length is exactly like that, a phrase that sounds sensible but describes nothing real. Others push back. They warn that we have been fooled before by declaring hard limits, only to find nature had more room than we thought. Maybe a future theory will show that the Planck length is important but not truly final, and that reality continues in some new form below it, playing by rules we have not yet dreamed. History gives them reason for caution. Walls in physics have fallen before. Scientists sit honestly with this uncertainty. That the Planck length marks a profound limit is widely agreed. Whether it is the absolute smallest size or merely the smallest we can ever access, remains unsettled and hotly discussed. It is one of those rare questions where the leading minds admit they do not yet know. What this reveals is deep. The Planck length may be more than a size. It may be the edge of the very idea of size, the place where smallness itself runs out of meaning, a boundary not just of distance, but of what distance can be. And a boundary, this fundamental, would ripple upward, touching things we thought were rock solid. Because if space has a smallest step, then one of the most famous rules in all of physics, the rule that nothing outruns light, might not be quite as simple as we believed. A minimum length could bend the speed of light itself. One rule in physics feels truly unbreakable. Nothing travels faster than light. It is the ultimate speed limit, woven into Einstein's picture of reality, tested endlessly, never once broken. Light sets the pace, and nothing beats it. But a smallest length could stir up trouble even for this sacred rule. And the trouble is subtle and fascinating. Here is the setup. Einstein's theory treats space as smooth, and in a smooth space, light of every color travels at exactly the same speed. Red light, blue light, all of it, moving in perfect lockstep. This is a cornerstone of how we understand the universe. Now suppose space is not perfectly smooth. Suppose it is grainy at the Planck length, with a smallest chunk, like the loops or pixels we explored. What happens to light crossing a grainy space? It might get jostled. Picture a smooth highway versus a road paved with tiny cobblestones. A car glides down the smooth highway at a steady pace. On the cobblestone road, it bumps and rattles, and its speed might vary just slightly depending on how its wheels catch the stones. Light crossing grainy space might behave the same way. The tiny grains could nudge it, ever so slightly, in a way that depends on its color. If that were true, then light of different colors might travel at very, very slightly different speeds through grainy space. High-energy light, with its tiny waves, would feel the grains more, like a small wheel catching every cobblestone. Low-energy light, with bigger waves, would ride over the grains more smoothly, like a huge wheel rolling across the same road, barely feeling the bumps. The speed of light would no longer be perfectly single and simple. The effect, if it exists, would be almost impossibly tiny for any normal trip. Across a room, across a country, even across the solar system, you would never notice. But across the universe, over billions of light years, those tiny nudges could pile up into a difference we might actually catch. So, scientists devised a clever test. Far off in space, violent explosions blast out bursts of light of many colors all at once. If space is grainy, the different colors, after crossing billions of light years, should arrive at slightly different times, the high-energy light lagging or leading the low-energy light by a sliver. Catch that tiny gap, and you would have caught the graininess of space itself. So far, the results point towards smoothness. The sharpest measurements show light of different colors arriving together in perfect step, down to astonishing precision. If space is grainy at the Planck length, the grains are either far finer than the simplest theories guessed, or arranged in a way that hides their effect. The cobblestones, if they are there, are smoother than we can yet detect. Scientists find this genuinely exciting because it is one of the rare places where the Planck scale might leave a fingerprint we can actually measure. We cannot build a machine to reach the Planck length, but we might read its signature in ancient light from across the cosmos. The hunt is real and ongoing, and it points to an even bolder idea. Some physicists suggest that a smallest length would not break Einstein's rules but upgrade them, adding a second unbreakable limit right alongside the speed of light. A new kind of relativity, with two cosmic walls instead of one. Let us step into that daring picture. Einstein gave the world a stunning idea. The speed of light is the same for everyone, no matter how fast they move. Chase a light beam as fast as you can, and it still races away from you at the full speed of light, unchanged. This strange truth reshaped our understanding of space and time. It is the heart of his theory of relativity. Now, some physicists propose a daring extension. What if there are two things that stay the same for everyone? The speed of light and a smallest length, the Planck length. They call this bold idea doubly special relativity, because it adds a second cosmic constant beside the first. Here is why this even comes up. Einstein's original theory has a hidden wrinkle when you bring in a smallest length. Imagine a tiny object, exactly one Planck length long. Now imagine someone zooming past it at high speed. In Einstein's theory, fast motion makes lengths shrink from the mover's point of view. So the racing observer would see that Planck length object as shorter than a Planck length. And that breaks the whole idea of a smallest, unshrinkable size. The flaw would depend on who is looking, which cannot be right if it is truly a universal flaw. Doubly special relativity fixes this with a beautiful move. It declares the Planck length to be the same for everyone, just like the speed of light. No matter how fast you move, you always measure the same smallest length. It cannot shrink below the Planck flaw, because that flaw is now a universal constant, woven into reality for every observer alike. Think of it like two speed limits on a strange highway. The first says you can never drive faster than a certain top speed. The second says you can never see a distance smaller than a certain tiny size. Both limits hold for every driver, no matter their speed, no matter their direction. Two walls, both absolute, both the same for all. This idea is elegant because it protects the Planck length as a true bottom. It keeps the smallest size, truly smallest, for everyone, forever, closing the loophole that plain relativity left open. And it does so by treating length the way Einstein treated speed, as a shared, unbreakable feature of the universe. But the idea comes with a price. To make two constants stay fixed for everyone, the math of space and time has to bend in new ways. Some versions predict those tiny color-dependent shifts in the speed of light we met earlier, which is one reason scientists watch distant explosions so closely. If doubly special relativity is right, its fingerprints might show up in that ancient light. Scientists treat this as a serious but unproven idea. It is one of several attempts to weave a smallest length smoothly into the fabric of relativity. It has clever supporters and thoughtful critics, and it lives or dies by evidence we are still hunting for, in the sharpest measurements of light from the deep cosmos. What thrills physicists about it is the vision, a universe with not one but two unbreakable limits, one for speed and one for size, both stitched into reality itself. It would mean the Planck length is every bit as fundamental as the speed of light, a true pillar of how the world is built. And thinking about limits this deep leads somewhere even stranger. Because if space and time have a smallest step, then maybe information does too. Maybe every fact about reality comes in tiniest possible pieces, with nothing finer allowed. Does information itself have a bottom? We have found a smallest length and a shortest time. Now let us ask about something less obvious, but just as deep. Does information have a smallest possible size? By information, we mean the raw facts that make up reality, where a particle is, which way it spins, the yes or no answers that stack together describe everything that exists. Scientists have learned that information is not just an idea in our heads, it is physical. It is woven into the universe itself, and it may come in tiniest possible pieces. The clue, once again, comes from black holes and the Planck length. Remember the shocking discovery from before. A black hole stores information on its surface, and that surface is divided into Planck-sized patches, each one holding a single bit. A bit is the smallest unit of information, a simple yes or no, a 1 or a 0. And nature seems to give each bit exactly one Planck-sized tile to sit on. This suggests something profound. Information may have a smallest chunk, just as space has a smallest length. You cannot squeeze more than one bit into a Planck-sized patch. There is a maximum amount of information any region of space can hold, set by its surface area measured in Planck tiles. Reality has a storage limit, and the Planck scale sets it. Picture a mosaic made of tiny tiles, each tile a single color, either black or white. From far away, the mosaic shows a rich, detailed picture, but you cannot add more detail than the tiles allow. Each tile is one dot, one choice, black or white. The picture can only be as detailed as the number of tiles. The universe may be a mosaic like this, its detail capped by Planck-sized tiles, each holding one bit of the cosmic picture. This flips how we think about reality. We tend to imagine the universe as made of stuff, matter, and energy filling space. But this view suggests reality might be made of information, of yes and no answers written in Planck-sized pixels, with matter and energy as the patterns those bits spell out. The world becomes, at bottom, a vast arrangement of tiniest possible fact, and it connects to everything we have seen. If information comes in Planck-sized bits, and space comes in Planck-sized chunks, and time comes in Planck-sized ticks, then reality starts to look like a colossal computation, a universe updating itself, bit by bit, step by step, at the smallest scale, following rules we are only beginning to guess. Scientists find this idea powerful and are actively exploring it. The link between information, black holes, and the Planck length rests on solid theoretical work that reshaped physics. How far the idea goes, whether the whole universe is truly built from Planck-sized bits of information, remains an open and exciting question. But the notion that information has a smallest size, tied to the Planck scale, is taken seriously by leading minds. So the Planck length may set the limit not just on distance and time, but on knowledge itself, on how much can be known or stored about any patch of reality. And a foam that boils with black holes, that stores information in tiny tiles, might do something even wilder with space itself. Some physicists wonder if the froth could open tiny tunnels, secret shortcuts linking places that seem impossibly far apart. Could the Planck foam be stitched with wormholes? We have pictured the Planck scale as a churning foam, space bubbling and popping, tiny black holes flashing in and out. Now let us follow one of the wildest ideas that foam inspires. Some physicists wonder whether the froth is threaded with tiny tunnels, shortcuts through space called wormholes. A wormhole is one of the most famous ideas in physics, a favorite of science fiction, but rooted in real theory. Picture space as a sheet of paper. 2 points, far apart, sit at opposite ends. Normally, to travel between them, you cross the whole sheet, the long way, but fold the paper so the 2 points touch and punch a tunnel between them, and suddenly they are connected directly, a shortcut through the fold. That tunnel is a wormhole. Now bring this down to the Planck scale. In the quantum foam, space is thought to twist and bend violently, forming and breaking tiny structures faster than any clock. Some scientists suggest that among those structures might be tiny wormholes, blinking open and shut, briefly linking distant patches of space through the froth. The foam would not just be bubbling, it would be stitched, moment to moment, with tiny tunnels weaving through the fabric of reality. These would be nothing like the grand wormholes of movies, the kind a spaceship flies through to cross the galaxy. They would be unthinkably small, around the Planck length, and unthinkably brief, gone in less than a Planck time. You could never send anything through them. Not a ship, not a signal, not even a single particle. They would be far too tiny and far too short-lived to be of any use for travel. So why do they matter? Because they might quietly shape reality in deep ways. Some physicists think a foam laced with tiny wormholes could affect how particles connect across space, or play a role in the strange links quantum physics reveals between distant particles. There are bold ideas suggesting that the mysterious quantum connection between far-apart particles might be related, at the deepest level, to tiny wormholes joining them through the foam. The tunnels would be reality's hidden plumbing, invisible but influential. Picture a calm lake seen from above, smooth and whole. Now imagine that just beneath the surface, countless tiny channels open and close, briefly linking one spot to another, over and over, faster than you could ever see. The lake looks placid and simple. Underneath, it is secretly threaded with fleeting connections. The fabric of space might be that lake, calm to us, secretly stitched with tunnels at the Planck scale. Scientists hold this idea as fascinating speculation built on serious foundations. Wormholes are real solutions in Einstein's theory of gravity, allowed by the math. Whether tiny ones truly fill the quantum foam, and whether they explain deep quantum links, remains unproven and actively debated. It sits at the daring edge of theoretical physics, more question than answer, but grounded in real science. What it shows is how rich the Planck scale might be. Far from a dull bottom floor, it could be a wildly active realm, boiling with black holes, threaded with tunnels, alive with structure we can barely imagine. And if the foam can stitch distant points together, some thinkers push the vision even further. They imagine the foam giving birth not just to tunnels, but to whole new universes, bubbling out of the froth like foam on a wave. Let us watch universes boil out of nothing. We have watched the quantum foam bubble spawn tiny black holes, and perhaps thread space with tunnels. Now brace for the grandest idea the foam inspires. Some physicists suggest that whole universes might boil out of it, bubbling into being like foam on a churning sea. The idea starts with what we already know. Our own universe seems to have burst from a tiny Planck scale beginning, expanding into the vast cosmos we see. Now, ask a wild question. If our universe could bubble up from the foam, why only ours? Why not others? Why not countless universes, each frothing out of the same deep chaos? This leads to a breathtaking picture. Imagine the quantum foam not just as the bottom of our universe, but as a vast, eternal froth from which universes are born. Every so often, in this endless foam, a tiny bubble forms, and instead of popping, it inflates. It grows. It blows up into an entire universe of its own, with its own space, its own time, maybe even its own laws. Our universe would be one such bubble among untold many. Picture a pot of water boiling hard. Bubbles form on the bottom, and most collapse right away. But some rise and grow, breaking the surface. Now imagine each rising bubble becoming its own separate world, sealed off, expanding forever. The pot of foam keeps boiling, endlessly, spawning bubble after bubble, universe after universe. Our entire cosmos, everything we know, would be a single bubble in that infinite boil. This is often called the idea of a multiverse, a reality far larger than our single universe, holding perhaps endless others. And the Planck scale foam is one proposed birthplace for them all. The smallest scale, the churning bottom of reality, might be the womb of worlds without number. The consequences stagger the mind. In some versions, these other universes might have different laws of physics, different strengths of gravity, different particles, different rules entirely. Most might be barren, unable to form stars or life. A rare few, like ours, might strike the delicate balance that allows galaxies, planets, and living things. We might live in one of the lucky bubbles, one where the numbers happen to work out for existence. This even offers a possible answer to a haunting question. Why is our universe so perfectly suited for life, with its laws tuned just right? If there are countless universes with countless different laws, then somewhere, by pure chance, one would come out right for life. And of course, we find ourselves in that one because we could not exist in any other. We live where life is possible, among perhaps endless worlds where it is not. Scientists treat the multiverse with real caution. It flows from serious theories about the early universe and the quantum foam, and many respected physicists take it seriously. But it faces a hard problem. Other universes, sealed off from ours, may be impossible to ever observe or test, and an idea we can never check sits uneasily in science. So, the multiverse remains a bold, fascinating, and deeply debated possibility, not an established fact. Still, the vision is awesome to hold. The smallest scale in our world might be the seedbed of infinite worlds, each one a universe, all boiling out of the same endless foam. And all this talk of pixels, bits, and bubbling code circles us toward an idea that has haunted thinkers for years. If reality is built from tiny pixels running by rules, then maybe reality is something like a program. Maybe we live in a simulation. We keep bumping into the same haunting picture. Space in pixels, time in frames, information in bits, reality updating step by tiny step at the Planck scale. And that picture leads to a question that sounds like science fiction but is asked, carefully, by serious people. Could our universe be a simulation? Here is what feeds the idea. We have seen that the Planck length might act like a pixel, a smallest chunk of space. The Planck time might act like a frame, a smallest tick. Information might come in Planck-sized bits, ones and zeros written across reality. Put these together, and the universe starts to resemble something familiar: a computer, a screen, a program running at unimaginable resolution. Think about a video game world. To the characters inside it, the world seems smooth and continuous. But the truth is that the world is made of pixels, updated frame by frame, run by code following fixed rules. If a character could zoom in far enough, it might hit the pixels, the smallest possible detail. It might find a smallest tick of game time. It might discover that its whole world runs on discrete steps. Some thinkers wonder if our Planck-scale discoveries are exactly what such a character would find, hinting that our world, too, might be a kind of program. The clues that tempt this idea are real features of physics: a smallest length, a shortest time, a limit on information, a speed limit for light, like a maximum processing speed, even the strange rules of the quantum world, where things stay fuzzy until observed, remind some people of a game that only renders detail when a player looks. These parallels are striking, and they are why the simulation idea refuses to go away. But here is where care matters enormously. These are parallels, resemblances, echoes. They are not proof. The fact that reality shares some features with a computer does not mean reality is a computer. Nature might have a smallest length for reasons that have nothing to do with simulation, reasons rooted in gravity and the quantum, exactly as we explored in every earlier chapter. A grainy universe and a pixelated game can look alike without being alike. Most physicists treat the simulation idea as a fascinating thought, worth pondering, but far outside proven science. It is very hard to test. What experiment could tell a simulated world from a real one if the simulation were perfect? Some researchers have proposed clever searches, looking for tiny flaws or patterns that a simulation might leave behind, like the fixed grid a game is built on. So far, nothing has turned up. Reality, as far as we can measure, behaves like reality. Picture a suspicion you can never quite confirm or deny. You notice odd coincidences, patterns that could mean something or nothing. You can build a case, but you can never reach certainty, because any evidence could have an ordinary explanation. The simulation question lives in that uneasy space. Suggestive, unprovable, endlessly debated. So the honest stance is open and humble. The Planck scale gives reality features that resemble a computed world. Whether that resemblance points to a real simulation or is just a curious echo of how gravity and the quantum shape the small remains unknown and probably untestable with what we have. It is a genuine mystery, held lightly by careful minds. What is clear is that the deeper we probe the smallest scale, the stranger and more question-filled reality becomes. And this leads to a sobering thought about our whole quest. We have talked all along about reaching the Planck length, seeing it, testing it. But we may never build a tool that can. The bottom of reality might stay forever beyond our reach. Throughout this whole journey, one hard truth has followed us like a shadow. We cannot reach the Planck length, not with our best machines, not with any machine we can imagine. And now let us face that truth fully, because it says something profound about the limits of human knowledge. We saw the reason early on. To probe the Planck length, you need energy so concentrated that it collapses into a black hole, erasing the very thing you tried to see. This is not a flaw in our tools. It is a wall built into physics itself. Any tool sharp enough to reach the Planck scale destroys its own target. The act of looking defeats the look. We saw how far our greatest machine falls short. Our mightiest particle collider, the pride of human science, misses the Planck scale by a factor so vast that to close the gap, you would need a machine the size of a galaxy, not a bigger lab, not a bigger country. A ring of magnets stretching across millions of stars. That is the scale of the challenge, and it is almost certainly beyond any civilization forever. So we are left knocking at a door we may never open. And this is a strange and humbling place for science to stand. We are used to progress, better tools, deeper views, walls falling one after another. For centuries, whenever we could not see something, we built a sharper instrument and saw it. Telescopes reached farther, microscopes reached smaller. The pattern felt endless. Give us time, and we will see anything. The Planck length may break that pattern. It may be the first hard limit on how deep we can ever see. A flaw set not by our cleverness, but by the rules of reality. Below it, the universe may keep its secrets forever, no matter how advanced we become. There may be a bottom to what can be known, and the Planck length may mark it. Picture standing at the edge of a vast fog that no light can pierce. You know something lies beyond it. You can reason about it, calculate around it, guess at its shape, but you can never walk into it and see. The fog is not a limit of your eyes. It is a limit of what can be seen at all. The Planck scale may be that fog, the permanent edge of the visible. Yet this is not a story of defeat, because even blocked from looking directly, science finds other ways. We cannot build a machine to reach the Planck length, so instead, we read its faint fingerprints in ancient starlight. We study black holes, where the Planck scale shapes the flow of information. We look to the early universe, which was once Planck-sized, and search its afterglow for clues. We chase the missing theory of quantum gravity, hoping math can take us where machines cannot. Locked at the front door, we search for windows. Scientists hold this with clear eyes and quiet awe. That the Planck length lies beyond direct reach is widely accepted, rooted in solid physics. Whether we can ever learn its secrets by indirect means remains an open, hopeful question. Human ingenuity has surprised us before, but the direct door may stay shut for all time. And so we come, at last, to the deepest question of all. After this whole journey down to the bottom of the small, what does it truly mean? What does the Planck length tell us about reality, about the universe, about our place in it? Does the cosmos really have a final, smallest piece? Let us find our way to an answer. We began with a simple act, shrinking a speck, smaller and smaller, chasing the bottom of reality. That journey has carried us to the strangest place in all of science. And now, at the end, let us ask what it all means. The Planck length has shown us wonders. A smallest meaningful size, woven into the universe by its own deep constants. a place where rulers collapse into black holes and distance itself dissolves. A boiling foam of space, threaded with tiny tunnels, flashing with micro-black holes born and dead in an instant. The birthplace of our universe, and perhaps the womb of countless others, the edge where our two greatest theories fall silent together, and where the missing masterpiece of physics waits to be found. Step back, and one truth stands above all others. The Planck length marks the frontier of human understanding. It is the exact place where our knowledge runs out and mystery takes over. Everything larger we can describe with breathtaking success, from atoms to galaxies to the whole sweep of the cosmos. At the Planck scale, and below, we stand at the edge of the known, peering into fog. Does the universe truly have a final, smallest piece? The honest answer is that we do not yet know for certain. Some evidence and some theories point to a hard bottom, a true smallest chunk of space, below which nothing exists. Other views hold that the Planck length is the smallest we can ever know, whatever lies beneath. Either way, it stands as a profound boundary, a flaw to reality or a flaw to knowledge, and perhaps both at once. Here is what should stay with you. For most of history, people assumed the universe was smooth and endless in both directions, as large as you please and as small as you please, with no walls anywhere. We have learned that reality has edges, a top speed, in the speed of light, and a bottom size, in the Planck length. The cosmos is not boundless in every way. It has structure, limits, a shape, and those limits are not roadblocks to curse. They are among the deepest truths we have ever found. Think of what this means for us. We are creatures of a middling size, far larger than the Planck length, far smaller than the galaxies. And yet, from our small perch, with our minds alone, we have reasoned our way down to the very bottom of the small. We cannot see it, we cannot reach it, but we have found it, named it, and glimpsed the wild strangeness it holds. That is a staggering achievement for a species that, not long ago, did not know atoms existed. And the mystery that remains is a gift, not a failure. The locked door of the Planck epoch, the unread first page of the universe, the unproven theories of loops and strings and holograms. All of it means the greatest discoveries may still lie ahead. Somewhere out there is a mind, maybe alive today, maybe not yet born, who will find the theory that reads the bottom of reality, who will finally tell us what happens when the universe reaches the Planck length. Until then, we stand at the edge, looking into the deepest fog there is, armed with wonder and a handful of impossible numbers. The smallest scale in the universe guards its greatest secret, and the search for that secret is one of the grandest adventures the human mind has ever begun. The bottom of reality is waiting, and we have only just started to look.